So far we have completed representing each and every node individual type, as well as we have also uh, written the class for representing singly linked list in our programmatic implementation, right? Now we have everything in place. Now let's get on with implementing the very first functionality, that is push functionality on a singly linked list. So generally what exactly this push functionality does is it will basically take the new value from the user and it will basically try to create a new node of type node that we have defined, and it will make sure that it is inserting that node at the end of the singly linked list. That means the end is exactly at the tail node, right? Because the tail value inside the singly linked list basically represents the very last node that we have, and obviously we have the tail node access as well inside the singly linked list representation that we are maintaining. So as part of the push operation, whatever the new node object that we create with the value that we take from the user, and it will make sure that it is adding that new node at the end of the singly linked list. But remember that, because we are adding a new node at the end of the singly linked list, whatever the tail node that we had previously, right, that will no longer be the new tail node. Whatever the new node that we have added will become the new tail node of the singly linked list. That is something that you have to remember. That means whatever the tail node that we are maintaining inside our singly linked list representation, right, we have to update it with the newly added node. Okay, so that is the simple definition. So what exactly we will do, we will take the value from the user and we will create the new node object of type node that we have defined, and we will make sure that we are adding it at the end of the singly linked list. So what all are the different cases that could come while implementing the push operation, right? So basically remember that, whenever you are adding a new value or new node into the singly linked list, right, there could be two scenarios. The first scenario is to check if the singly linked list is empty, and the second check would be to check if the singly linked list is not empty. Whereas when you are trying to remove the value from the singly linked list, right, then there will be three scenarios. First scenario is basically the singly linked list can be empty, and the second scenario is basically where we have only one node, and the third scenario is basically where we have more than one node inside the singly linked list representation. Since here we are introducing a new value onto the singly linked list, right, so obviously the first case would be to check if the singly linked list is empty, right? Obviously when the singly linked list is empty, whatever the head node and tail node that we are maintaining, right, in the case of Java or JavaScript representation, we are maintaining null value in it. Otherwise, if we are trying to do it Python based implementation, right, in that case we are storing none in it. In both head and tail we have null. In the case of Python implementation we have none. Similarly inside the length we are having 0. So whatever the new value that I am adding into the singly linked list, that will be the only node that will be present inside the singly linked list, right? That means whatever the node that we have added will become the head node as well as the tail node. So we have to make sure that we are updating the head with the new node that we have added. Similarly, tail node also we have to update it with the new node that we are adding, because we have only one node in the singly linked list. That means that itself is the head node and tail node. That's why inside the head value and the tail value we are maintaining, we have to make sure that the reference of new node is getting updated inside that. Similarly, since we are adding a new value into the singly linked list, we need to increment the length by length plus 1. Okay, so that is the first scenario where head and tail were not there. That means the singly linked list is empty. Now let's try to understand the second scenario where we have a non-empty singly linked list. So non-empty singly linked list case is what we have here, right? Obviously here we have some number of nodes already available inside the singly linked list, and we have the head node and we have also have the tail node. So each and every node has some value in it. Let's say 10, let's say k, let's say true or something like that. Now let's just say I want to add or I want to push the value, let's say code, onto the singly linked list. So what I will do is, we already have the reference of the head tail node, right? So from the tail node, the existing next pointer in the tail is, at this point of time it is null if you are doing Java or JavaScript based implementation, if it is none if you are following the Python based implementation. So here we will basically create a object, node object with the value code, and we basically update the reference of the existing tails next to newly created node. That means in the existing tail node we have the reference of the newly created node as well. So we have adjusted the next pointer of the existing tail, and obviously the next on the newly added node is, obviously it is empty. Now this, whatever the true node that was there, will no longer be the tail node of the singly linked list, right? So what we have to do, we have to update the tail node to the newly added node, that is code. That means whatever the tail reference that we are maintaining inside the singly linked list, right, it should be updated with the new node that we are adding. In this case we will not do anything with the head because we had certain number of values inside the singly linked list. That means head is somewhere but the tail is somewhere, and to that tail node we are adding a new node as part of the push functionality. So we will not do any changes to the head node, we will simply update the tail node with the newly added node, and we will also increment the length by 1. Okay, in this way we are keeping consistency in the tail node because we are adding a new value into the singly linked list after the end, and we are adding a new node into the singly linked list, right? That's why we are incrementing the length by 1. So that is how we are maintaining the consistency across the variables we are maintaining inside the singly linked list representation. Okay, now according to the algorithm that we have discussed, right, for various cases on a push operation, now let's try to write the pseudocode for the same. So inside the pseudocode, what exactly we are doing, we basically define a function called push function, and this function will basically take the new value from the user. So for as part of the first step, we have already defined the node class, right? So we basically create the node object with the value that user has passed, be it empty singly linked list, be it non-empty singly linked list, we have to have the object of node first. Based on that, based on whether the singly linked list is empty or based on the singly linked list is not empty, we will try to perform the operation, right? So after creating the object, what we will do is we will check if singly linked list is empty. How we will check? If you are doing Java or JavaScript implementation, right, inside the head, when we created the object of singly linked list, we have assigned null, and inside the tail also we have assigned null, and inside the length we have assigned 0. If you are following Python based implementation, right, inside the head node, null equivalent is none, right? So we have defined head with none. Similarly, we have defined tail also with none, and length we are maintaining 0. Now if the singly linked list is empty, in the case of Java and JavaScript implementations, head and tail will be pointing to null and the length of singly linked list will be 0. So based on that, we will be able to decide if the singly linked list is empty or not. Now anyway, that algorithm I have already explained, just that I am trying to give much more context here. So if at all, if the singly linked list is empty, right, whatever the new node object that we have created will be the head node. So head node, we will update it with the new node object. Similarly, since that is the only one node, we will make sure that tail node also is getting updated with the new node object that we have created. And after that, we have to increment the length by 1. Increment length by 1. In the end, we will simply return the node that we have added. That is, whatever the new node object that we have created, we will return that. So this is the case where the singly linked list is empty. If at all, if the singly linked list is not empty, right, that means it is not empty. In the case of non-empty singly linked list, we already had the reference of the tail node inside the singly linked list containing some number of values. So inside the tail node, obviously the next reference was empty. So we have to make sure that since we are adding a new node, this node's reference should be present as part of the existing tail node, right? So first we will read the tail node. Okay, so in this tail node we will basically update the next to new node. Okay, that means we are adding this object reference into the existing tail node. After updating, we have successfully added the new node into the singly linked list, but the tail node is still pointing to the old last node that we have inside the singly linked list. So the tail node should be updated to the very last node we have in the singly linked list. To do that, what we will do is we will simply update the tail node to the new node object that we have added. Similarly, in this case also, we have to increment the length by 1. In the end, we will simply return new node object. Okay, so this is the pseudocode for implementing the push functionality on a singly linked list. So remember that there will be two cases. One will be empty singly linked list and the other will be non-empty singly linked list. Okay, so that is how we perform the push functionality, and let's go ahead and let's try to implement it programmatically as well. So right now what I'm doing is, anyway we have written the singly linked list class previously, right, where we tried initiating the singly linked list object and made sure that it is a empty value, it contains no values pointing head and tail to null and length to 0. Now our job is to write a separate push function and make sure we are handling all the scenarios that could come as part of the push operation. So for that I'm trying to write a separate function. I will call the function as push, and this function will basically take the new value that user wants to insert at the end of the singly linked list. So I'll take the value that user is passing inside the variable value. Okay, so as part of the first step, what I will do is I will try to create the node object that we are going to store as part of the that we are going to add in the end. So for that node we need to use the node object that we have created earlier, right? So to use that, I'm simply going to, from node class node.py file, I'm just going to import the node class that we have written. Okay, so from the node.py whatever we have written, I'm importing the node class that we have already written in the previous videos. Once I have that, I will simply create an object of that node with the value that user wants to store in the end. How will I do? I'll simply create an object new node equal to node of. To this I need to, this node object constructor is init function is basically taking the value that I want to store as part of the current node, right? For that, whatever the value that user has passed, I'm going to pass that value. Okay, so here I have the new node object that I can insert at the end of the singly linked list. But the thing is, as part of the algorithm and pseudocode, if you remember, there are two scenarios, right? One is we either try to push the value into an empty singly linked list, or we try to push the value into a non-empty singly linked list. So we have to honor those two scenarios in the implementation. So how will we do that? We know that singly linked list is empty if either head or tail is null, and if the length is also 0, then we know that the singly linked list is empty. So what I will be doing here is, from the current object I am going to read the head. If it is none, then the singly linked list is empty. Here you could simply use the self.tail equal to none also you can do. You can also do self.length. If it is 0, that means that there are no nodes in the singly linked list. You can use either of them. I am going to use, if the head reference is none, that means that there are no values inside the singly linked list. If this is the case, what I will do, whatever the new node that we are adding, that itself is the head node as well as tail node, because there is only one node in the singly linked list. To do that, what I will simply do is self dot head is equal to new node, and along with this I will also do self dot tail also to the new node that we have created. Okay, this is the case where there are no nodes in the singly linked list. Otherwise, if there is a case where there are already some number of values in the singly linked list, and to that I'm going to add the new node at the end. In that case, at this point of time, we have the current tail node. Here we have the new node that we want to add. So to adjust the next reference, what we have to do, from the current tail nodes next, we need to update it with the newly added node, so that we will not lose the reference of the newly added node. So to do that, what I will do is self dot tail will basically give the current tail node of the singly linked list. From this tail node, we have the reference to the next node. How we will get, which is nothing but next. We will simply update it to new node. But we are not done here. So we are adding the node to the existing tail node, right? That is, whatever the new node that we have added will be the new tail node of the singly linked list. So to do that, I'll simply do self dot tail equal to new node that we have created. Okay, if you remember, we are also keeping the track of length of the singly linked list, right? That is how many number of nodes are present. So either if the singly linked list is empty or non-empty, we are ultimately adding one node into the singly linked list. That means that length should be incremented by 1. So to do that, self dot length, I am going to update it with self dot length plus 1. Okay, in the end we need to return the new node that we have added, which is available at return self dot tail node. Okay, or you can simply return new node also, because in new node itself it is becoming like a tail node. So this is how we honor two cases where we are trying to push the new value into an empty singly linked list and non-empty singly linked list. Okay, now let's try to call this function and see if it is actually persisting the values or not. Okay, so for that I'm just going to remove the print statements that we have written as part of the singly linked list initialization. Now we have the reference of the singly linked list object here. From this, all I have to do is SSL dot push of, let's say 10. Simply SSL dot push of, let's say codingpal.org. Okay, you know that singly linked list should hold any type of the data, right? That's why I'm trying to push different values into the singly linked list. Okay, so let's say I want to store a boolean value. Okay, you can pass any type of the value and it will automatically store in it. Okay, to validate if it is actually storing the values in the order that you are passing, and that based on the type also it is not restricting and all those things, you will be able to validate it if you are able to traverse all the values from head node till the tail node. This traverse function itself is like a separate functionality that we will be implementing later on, and in the next video specifically, once I implement it, you will be able to validate the values that we have passed to the push functionality here. Okay, in the next video we will be implementing this specific traverse function, but at this point of time don't worry about the validation. It will definitely work because we have successfully handled the two scenarios where the list could be empty and the list could be not empty. Okay, that's all for this video. I'll see you in the traverse function implementation. Now we have written the programmatic implementation of push functionality as well, right? Now let's just try to understand the time complexity and space complexity involved in performing the push functionality on a singly linked list. To handle the both scenarios, even if we have n number of nodes in the singly linked list or even if the singly linked list is empty, what exactly we are doing? First step, we are basically creating the object of the new node with the value that user has passed, right? So obviously for that creation of object, we will not take more than 1 unit of time. Similarly, in the case where we don't have the nodes at all inside the singly linked list, right? Exactly, we are simply updating the head node and tail node with the new node that we are creating. Since these are simple, assignment operations, and incrementing the length also is a simple assignment operation, right? These operations will take 1 unit of time itself. As a result, when we don't have any nodes inside the singly linked list, the time complexity will be order of 1 only. Similarly, even if we take the case where we have certain number of nodes inside the singly linked list, that means the singly linked list is not empty, right? In that case also, we are maintaining the reference of the tail node in our singly linked list representation. That means inside that class that we are maintaining for singly linked list, we can directly read the tail node. That read operation is obviously is going to take 1 unit of time itself, and after that we are updating the next reference of the current tail node with the new node that we are adding. So obviously this is also a simple assignment operation, and it will take only constant amount of time. In the end, just like how we handled updated the tail reference and incremented the length by 1, right? Then these are also simple assignment operations, so these will also take constant amount of time. So as a result, even if you take the case where we have certain number of nodes available inside the singly linked list, the time complexity will be order of 1 only. And if you take the space complexity, obviously the only space that we are consuming is basically to create the new node with the value that user has passed. Obviously we can't skip that node object creation, right? And we won't consider that as a memory consumed by the algorithm that we are using for performing the push operation. So obviously the memory that is consumed by creation of node object will also be constant. And if you take the case where we don't have any nodes inside the singly linked list, we are simply updating the reference of the head that we have already have inside the singly linked list and tail with the new node. So these will obviously simple assignment operations, and they will not consume any more memory internally, right? As a result, overall memory consumption in the case where the singly linked list is empty, right, it will be constant. That is, it is order of 1 only. Similarly, if you take the case where the singly linked list is not empty also, we are not consuming any memory, we are simply performing the assignment operations, and these assignment operations will not take more than a unit of memory, right? That's why in this case also the space complexity will still remain order of 1 only. Okay, so that is all with respect to implementing the push functionality on a singly linked list. In the next video, let's talk about the pop functionality on a singly linked list, where we try to delete the very last node we have inside the singly linked list.